For section 3.3, we are going back over and applying the things that we've learned to some business situations. We've already reviewed the basics here. Revenue, cost, and profit. We know by now that revenue is the total of the money that we bring in. And revenue is not the same as profit. To find revenue, we multiply the price of an item times the quantity. Cost is how much we spend, how much money goes out. So we've got revenue is money brought in, cost is the money spent. Now, when we calculate cost, we have to calculate the fixed cost as well as the variable cost, where the variable cost is the cost per item. The fixed cost is a fixed cost, whether we make one thing or a million things. And then profit, finally, is that difference between our revenues and our costs. So we've got our revenue function, our cost function, and our profit function. Okay, that variable cost is where we end up with our marginal cost. That marginal cost is the rate of change of the cost function. So for a linear cost function, it's going to look like this, where B would be your fixed cost. M is that slope of the cost line. The amount that is spent per item, that's our marginal cost. Good definition here, that marginal cost is the cost of producing one more item. And then we have marginal revenue, which is the rate of change of our revenue function. If it's a linear revenue function, again, it's in our mx plus b form. That marginal revenue, k, the slope of the revenue function, is the revenue from selling one more item. So the amount of money that we bring in for one item is our marginal revenue. The amount of money that we spend on just one item is our marginal cost. Okay, here's some examples. We've got a trailer hauling service, and it charges $95 plus $8 per mile. Well, what have we got? We've got two different types of charges. We've got $95, so if you are going to pay someone to haul a trailer somewhere for you, then you're going to pay them $95 just to schedule it. And after that, it depends on how far they have to take it, because they're going to charge $8 per mile. Well, X here is going to be the number of miles that we're going to travel. That's $95 is our fixed cost, because we're going to pay them $95 if we schedule no matter what. And then the $8 per mile is our variable cost, because if I'm just going 5 miles, it's only 40 bucks here. But if I'm going 500 miles, it's going to be $4,000 there. So my cost function, C of x, is going to be, and if we write it in slope-intercept form, linear slope-intercept form, y equals mx plus b, we're going to have that $8 per mile, where x is the number of miles, plus the fixed cost of $95. And then we're asked to find the cost for a 100-mile trip and a 101-mile trip. So if we plug in 100 miles for x, we've got 8 times 100 plus 95. Well, that's going to be $895. And if we go just one more mile, 101 miles, we've got 808 plus 95, which gets us to $903. And that difference right there, the difference between 100 miles traveled and 101 miles traveled is $8. That's my marginal cost. Now this cost function is linear. We always want to kind of have in the back of our minds what the graph would look like. We want to think about that graph. The cost function is linear, and we know the further we go, our input is x, miles, and the further we go, the more it's going to cost. So we're going to have a line with a positive slope. We also know from our slope-intercept form that this is going to give us our y-intercept. So when I'm setting up my graph here, let's do what are we going to do? Let's do 30, 60, 90. That would be 120. I'm counting by 30s. This is going to be the cost in dollars. If I go 0 miles, if I just hire them, my intercept is at 0.95. Now I went a long ways here. So these values don't give us points that are going to show up on the graph that I created. Let's say, so this would be 0 miles, 5 miles, 10 miles, 15 miles. Well, if I go 5 miles, 8 times 5 is 40, plus 95 is 135. So 5 miles out is going to be up here about 135. I see that I've got this linear slope with a y-intercept at 95. 0 miles is going to cost me $95. 5 miles is going to cost me $135. Okay, let's move on to the next one. Assume that the cost and revenue functions are linear, because that's what we're most comfortable with right now, are those linear functions. We're given a fixed cost, a marginal cost per item, and told that the item sells for $80. Now I encourage you to pause the video, see what you can do with this on your own, and then come back to check and see how you did. My cost function is going to be my fixed and my variable cost. We're going to go ahead and put it in slope-intercept form, y equals mx plus b form. So my cost function, c of x, that marginal cost per item is going to be $30 per item times x, and then my fixed cost is $17,000. So there's my cost function. This is my variable cost. This is my fixed cost. And this is going to give me my income or my revenue. One item, that's the cost per one item, is my marginal revenue. This is my variable cost. We can also call it our marginal cost. Oh, you got it right there, sorry. Revenue function right here. R of x is going to be 80x because each one sells for $80. My profit function, I take that revenue function and I subtract the cost function from it. So I take all of my income, 80x, and I subtract from that, don't forget your parentheses, your cost function. Because when you subtract the entire function, that negative has to distribute to that second term. So I've got 80x minus 30x puts me at 50x minus that $17,000. So I'm charging $80 per item, but it cost me $30 per item to make. So the profit per item is $50, but then I have to subtract out of that profit my fixed cost. So let's look at this last one. The profit on 100 items. There's my profit function. The profit on 100 items. I'm bringing in $50 per item once I take out my marginal cost from my revenue. So I'm bringing in $50 for those 100 items, $50 per item for those 100 items, but then I've got to subtract out my fixed costs. So when I subtract this out, this ends up being 5,000 minus 17,000. If I only sell 100 items, I am in the hole $12,000. I've got a loss. Anytime you come up with a negative on that profit, that represents a loss. All right, let's look at the next page. Again, I encourage you to pause, see what you can do on your own, and then come back and we will go over. Assume that the given situations can be expressed as a linear cost function and find the appropriate cost function. Oh, so that's all we're doing here is finding a cost function. Well, if we've got a fixed cost, we've got we don't have a marginal cost. We know that to do 40 items, it's going to cost us $5,000. Now, out of that $5,000, we need to find our marginal cost. We need to find our marginal cost in order to get our cost function. So out of that $5,000, $2,000 of it is fixed cost. So that means that $3,000 is the variable cost for 40 items because that's how many we produced. Well, if $3,000 is the cost to produce 40 items, the variable cost to produce 40 items, I can divide that. 3,000 divided by 40. That would cancel. I've really got 300 divided by 4. If you plug that into your calculator, it comes out to be $75 per item. That's my marginal cost, $75 per item. Now my goal here is to write the cost function. So my cost function is that marginal cost, $75 per item, plus the fixed cost that I was given. There's my cost function for this. All right, now that we've done one together, repause, go back and see what you can do with this one. Make sure you can follow along. Again, we're given marginal, not again. This time we're given marginal cost instead of fixed cost. And we know that 150 items cost $16,000 to produce. We need to find the fixed cost this time. So what do we need to do? Well, marginal cost is $90, and we're going to make 150 items. So my variable cost, $90 times 150 items. You put that into your calculator, you get $13,500 for the variable cost part to produce 150 items. So then when I look at that difference, I can find my fixed cost. I see that 16 minus 13,500 gives me $2,500 for my fixed cost. And now that I know both marginal and fixed cost, I can put together my cost function. My marginal cost is 90 per item, and my fixed cost is that 2,500. So I start with what I know, and I reason through the best way to put things together to find what I don't know. Now we've got a new concept here, average cost. Well, you know how to find an average. You find your average test grade, you add them all up and divide by the number of tests, right? Well, you're going to do the same thing to find the average cost. You're going to divide the fixed cost equally among the number of items produced. You're going to divide the fixed cost equally among the number of items produced. So for example, if it's going to cost me $1,000 fixed, and I'm making shirts, and I need to buy $10 worth of supplies per shirt. Well, if I make one shirt, it's cost me $1,010. If I make two shirts, it costs me $1,020 because 2 times 10 plus that fixed cost, 1,000. So, and what if I make 5 shirts? 5 shirts. Well, that's going to be $50 here, so that would be $1,050. Well, my average cost per shirt, if I'm just producing one, the average cost is $1,010 per shirt. If I produce 2, the average cost per shirt is $1,020 divided by 2. Now it's just $510, just $510. If I produce 5, my average cost per shirt, that $1,050, now I'm dividing out that fixed cost among 5 shirts, and it goes down to $210 per shirt. So the more items I make, the more I divide out the weight of the fixed cost so that it gets shared amongst more items and that it goes down as far as cost per item. Alright, let's do an example of these. We've got a cost function. C of x is 80x plus 12,000. So our fixed cost is 12,000. If we only make one thing, the average cost is the cost per item, $12,080. That's a lot, right? Let's see what happens if we produce 100 items or if we produce 1,000 items. Now we're going for average cost per item. So if I produce 100, the total cost is going to be 80 times 100 plus 12,000. that total cost comes out to be $20,000. I'm dividing it among 100 items to find my average cost. So the average cost per item here, 20 divided by 100, comes out to be $200 per item if I make 100 of them. What if I make 1,000? Well, the cost for 1,000, now I'm doing that 80 times 1,000, still adding the 12,000 in, I get to $92,000. But when I go to find the average, this time I'm dividing out by 1,000, so that the average cost per item comes out to be just $92 per item, because when I produce more, that fixed cost is divided out over more of the items. So does the average cost increase or decrease as the number increases? Well, that's what we just said. It decreases. That average cost per item decreases because the fixed cost is spread out and shared over more items. Think about it this way. If you want to take a trip, gas prices right now are really, really high. If you want to take a trip and just one of you goes, it may cost you $200 in gas. But if you can get 3 friends to go with you, 4 of you are going in the same car, you're just out $50 each for gas. That's a lot more affordable. So we are spreading out that fixed cost. Find the average cost function. Well, average cost, if I put that bar over C, that's my average cost notation. The average cost is the total of the cost function divided by the number of items. So let's think about a graph of this average cost function and see if it is increasing or decreasing. Now, when we do our graph of our cost function, we're going to have a number of items as our horizontal axis. We are going to have average cost in dollars as our vertical axis. Now we got 2 points we want to put on our graph. So we know we want to go up to 200. So let's do maybe 50, 100, 150, count by 50s. $200 up here. And then number of items, we did 100 and we did 1,000. So if we do count by hundreds here, 100, 2, 3, 4, 5, 6, 7, 8, 9, and then that would be 1,000 items. We calculated 2 points. We got an average cost per item, 100 items is $200 per item. That's our first ordered pair. 100 items is $200 per item. Our second ordered pair, 1,000 items, is going to be $92 per item, which is going to be roughly right there. And we can draw this as a linear function. Is it linear? Maybe not. It could slope. We're not sure. But what we are sure is that it is decreasing. Okay, next page. Depreciation. Now, this is something that if you have ever bought a car that you are aware of. Most of the things that we purchase in life are going to depreciate as we use them. They become less valuable. Now, right now, a big exception to that would be a house. If you buy a house, housing prices are increasing in value. They're appreciating. But depreciation is the rate at which an item loses value over time. How fast an item loses value over time. We talk about cars depreciating in value. I'm going to hit my autofocus button. It's going to fade out in a minute for a second. We talk about cars depreciating in value. For businesses, a lot of their equipment is going to depreciate over time. So they have to plan ahead to make sure they replace those things. Depreciation usually has a linear graph with a negative slope. And I mentioned this, but just so you have it set aside, If something appreciates, appreciation means it gains value over time. So it would have a positive slope if we were to graph appreciation. Okay, but depreciation is usually the situation that you're working with in business. A manufacturer's suggested retail price, MSRP, for a base model 2016 Toyota Prius at the time that this problem was written was $25,035, and it was expected to be worth $14,115 4 years later, so it has depreciated in value. We can write two ordered pairs to the model the data. That the independent variable is going to be the time. So we can do either years or we can do date. Let's go ahead and do date and say, okay, 2016, the Prius is worth $25,035. And then in 4 years later, so that would be 2020, it was expected to be worth $14,115. So there's two ordered pairs. Find a linear depreciation function for this car. Well, first, let's go ahead and sketch a graph real quickly. If I do 2016, actually 2016 should be here. 2016 is my starting place. 17, 18, 19, 20, 20, 4 years later. We're up at 25,000, 5, 10, 15, 20, 25,000, just over 25,000 here. And by 2020, we are down to 5, 10, 15, less than 15,000. So there would be my linear model of the depreciation in value for this Prius. Now it asks us to find the function, depreciation function for this car. Well, this line has a slope. It has a negative slope. So let's find that slope. M is going to be change in y over change in x, rise over run, or in this case fall over run. Where if we start with value here, y values go in the numerator. That should be a comma. Minus 14,115. And then my years, I get $10,920 over 4 years' time, and it's negative. My slope is negative because it's depreciation. We see that we have a depreciation slope of $2,730 per year. That's my slope. Estimate the value. So what is the rate? Right there. It's losing about $2,730 in value per year. That's the rate the car is depreciating. The rate is my slope. What's the value of the car 5 years from now? Let's change that to purchase date. 5 years from 2016. So if I find the depreciation value in 5 years, I would start with the purchase price and subtract that rate of depreciation times 5. If you plug that into your calculator, you should come up with a value of $11,385. Now, stop and think if this makes sense. 4 years after purchase, it was worth $14,115. 5 years after purchase, yes, it does make sense that it would be worth $11,000. That's almost $3,000 less. Okay, let's look at the next one, break-even point. I think that we've already discussed break-even point. Break-even point occurs when our income matches our outgo, when revenues match cost. At the break-even point, for whatever number of items that is, our profit is $0, but we are not in debt. So our break-even point is when, and another way to say this, break-even point would be when revenues minus cost equals 0. There's a third way to write our break-even point. All right. The owners of a parking lot have determined that their weekly revenue and cost in dollars are given by the formulas below, where X is the number of long-term parkers. X is my long-term parker numbers. So this is my revenue per parker. So they're paying $80 a month to park. And this is the cost function. It costs $50 per long-term parker plus a fixed cost of $2,400. That could be the rent for the parking garage, it could be the mortgage on the parking garage, whatever it is. That's our monthly fixed cost. Our marginal revenue is the income per parker, per long-term parker. That's my $80. The marginal cost is how much it costs them. That's probably going to be like electricity, security guards, that kind of stuff is going to be marginal cost per long-term parker. Fixed cost is that $2,400. It's going to cost that per month for them, whether they have 5 long-term parkers or 500 long-term parkers. Now, one thing that this doesn't give us is the capacity of the parking lot, so that would be something interesting to know. Find the break-even point. Well, the break-even point, I can either set it up like this. I can say revenues minus cost equals 0, or I can set up revenue equal to cost. If I choose to set up revenue equal to cost, I subtract my 50x from both sides. I get that 30x is equal to 2,400, and I'm going to need to divide by that 30 to solve for x. When I divide 2,400 by 30, I get x equal to 80. That's how many long-term parkers they need to break even. Now, that's my break-even point. So at break-even point of 80 long-term parkers, that means their profit is 0. So the break-even point, where x is 80, they have made $0, but they're not in debt. They're breaking even. So with 80 long-term parkers, they have $0 of profit. Would you expect a profit or loss with 60 long-term parkers? Well, hopefully it makes sense to you that you're going to have a loss, because if they've made it to 0, broken even at 80, 60 is less. So that's you haven't met your break-even point. That's below your break-even point. Find the profit function. Plug in. Now we set this up here, but we didn't plug it in. So let's find the profit function. P of x is revenue minus cost. So 80x minus, and don't forget your parentheses there, 50x plus 2,400. And then that becomes 30x minus 2,400. So that's my profit function. If I actually plug in 80 long-term parkers here, 30 times 80 minus 2,400, 2,400 minus 2,400 is my $0 profit. So that helps us to verify that we got the break-even point correct. All right, that was a good introduction to that one. Let's look at our last page. The accounting and sales department have provided cost and sales estimates on a new product, and you have to analyze the data they give you, determine what it will take to break even, and whether or not to go ahead with production. Now, just like I mentioned, how big is your parking lot? How many parkers can you have? That's an important thing to consider. With this new item, you can't sell more than 400 units, either because of facilities limitations like the parking lot, or production limitations, whatever it is. You're not going to be able to sell more than 400 units. So if I check my break-even point, what would it take to break even? I can set these functions equal to each other. I think like I said, there's more than one way to do this, but I think this is probably the easiest, at least for me. So my revenue function, when does that equal my cost function? I want to solve for x to see how many units that would take. So 15x equals 7,000. And if I divide both sides by 15, this is not going to come out nice and even for me. So let's go ahead and let's show that on the calculator. This fraction is just a division problem. 7,000 divided by 15 comes out to be 466 point, and then 6 is repeated. So I can say x would be 466.6 repeating. So that's my break-even point. Now the question we're asked, do we want to go ahead with production? Well, hopefully your answer is no. You cannot break even. And you cannot break even because we've been told that there's only 400 units available. Okay. Supply and demand curves and equilibrium point. Now this is just kind of an interesting thing that we're going to discuss for a couple of minutes. You're not going to see this a lot, but these are some good terms to notice and to think about. We're going to use P for price and Q for quantity. That's the number of items. A surplus of supply is when supply exceeds demand. Right now, I'm doing this in the summer of 2022. A good example would be masks and hand sanitizer. Supply exceeds demand. What's going to happen when supply exceeds demand? Well, we're going to look and see. Shortage of supply. Shortage of supply is when demand exceeds supply. Everything during the pandemic, masks, hand sanitizer, Rotel, so many groceries were in short supply. Shortage of supply is when demand exceeds supply. Now my equilibrium point is when those two things balance out and supply equals demand. So if you look at our graph here, we've got supply, and this is my supply right here, and then we've got demand, and this is my demand function right here. This is my supply function, that one's my demand function. And you can tell, hopefully, that right here where they are equal, we have our equilibrium point. Equilibrium point. That equilibrium point occurs when we've got a supply of 10 units, priced in dollars, and we're pricing each unit at about $120. So my equilibrium point would be when we've got 10 units priced at $120, supply is equal to demand, and we're happy. So that's my equilibrium price, is $120. How many people are willing to pay $140 for the product? Well, my price here at $140, this is my demand line, my $140 right here. It looks like there's, oh no, how about right here? It looks like there's about 3 people who are willing to pay $140 for whatever we're making. Do they benefit from that equilibrium price? Well, yes, right? Because the equilibrium price would be less than that. They would save money. How many people are willing to sell for $140? So here we're looking at our supply line, and our supply line hits this $140 mark way over here, right here, at 20 people. Our supply line hits $140 at 20 people. So lots of people are willing to sell at $140 price point. Are they going to benefit from the equilibrium price? Well, no, because they're trying to sell at higher than the equilibrium price. Even though there's 20 people wanting to sell, there's only 3 people who are interested in buying. So no, they actually lose money because people aren't wanting to buy at that price. How many people are willing to pay $100 for our item? Well, demand line at 100, right here, demand line at 100, it looks like right here at 16. So 16 people would be willing to pay to buy at $100. Would they benefit from the equilibrium price? No, it's more than they want to pay. So if there's a sale on, more people are willing to buy. How many people are willing to sell for $100? Well, 6 people want to buy, 16 people want to buy. How many people are willing to supply at $100? Well, that's over here, nobody. No one is willing to sell at $100. So you've got a big demand for the item at $100, but no one's willing to sell it at that price. All right, excellent.